Hi everyone and welcome to my YouTube channel. In this video we'll be discussing the RMO 2023, which is the Regional Mathematical Olympiad in India. So first of all, you go to the IOQM, and after the IOQM, by the way, we already did the IOQM paper for 2023 on the channel. After the IOQM, you go to the RMO, which is of course a proofwritten paper, as you can see, unlike the IOQM, which was you just need to write the answer to the question, 2-digit number. Okay, after the RMO, you qualify to the INMO, which is the National Math Olympiad. Of course, the difficulty is way harder than that. And after that, you, I believe you go to the some camps, and then you simply go to the team selection test, and you go to these 6 students representing India in the IMO. So let's look at the general rules here. We have the time is 3 hours, and maximum marks is 102. So that means since we have 6 problems, each problem I think it's worth 17 points. Yeah, I guess that 17 times 6 is 102. And basically it's just a proofwritten exam, so you just need to solve each one and write here. They should look at the style of your writing. Your writing should be good here. It's not just a multiple choice exam. Okay. By the way, we already did this paper on our Discord server, so make sure you join the Discord server where we're uploading each week one practice paper. So you can go there and try the papers that we were posting each week, and of course post your solutions or ideas, and of course you can chat with other nice guys there on the Discord server. So make sure you join it. Alright, so my dear friends, what are we waiting for? Let's get started. So the first question here is, we're given that n is the set of natural numbers, of course, positive integers, and they're telling us a new set S. They're defining it as the set of all 4 tuples, basically a, b, c, d, such that a squared plus b squared plus c squared is equal to d squared. And we were asked to find the largest positive integer m that divides a, b, c, d for all a, b, c, d in S. Okay, so in these types of questions, what we should do is simple. First of all, we should try to find the value of m, to guess it basically, to guess a value for m. How do we guess the value? Of course, we plug some values that satisfy the equation in ABC for a, b, c, and d. After that, after we guess the value, we need to do 2 things. We need to show that it works. That means m indeed divides any a, b, c, d. I mean the a, b, c, d thing for any value a, b, and c, and d in S. And then we need to show that it's the largest. That means there is no larger value for it. Okay, so first of all, the first thing that we should try to do is bring some examples. So let's try to substitute some a, b, c, and d that satisfy this equation: a squared plus b squared plus c squared is equal to d squared. Alright, so the simplest thing you can try for d. Of course, d cannot be 1, because this thing here is at least 3. D, if you set d as 2, then 4, you cannot write 4 as sum of 3 squares here. What about these 3? These 3, it's 9. Can you write 9 as a sum of 3 squares? Well, you can just put 1 and 2's. So for sure you can. You can simply choose this a, b, c, d. You can choose it as 1, 2, 2, 3. So we already found one example, which is really good. So here, that means if we take ABCD, what is ABCD? ABCD is just 12. So that automatically means that m divides 12. Now this thing is very nice, because that means that m must be a divisor of 12. So it can be 1, 2, 3, 6, or 12 itself. Okay, the question is, maybe m is 12 itself. So to work with this question, we need to do 2 things. like right now our goal is to show that M divides ABCD for any for any ABCD that satisfy this. So if M was 12 right now, depending on this, M can be 12. If we can show that 12 divides ABCD for any A, B, and C, and D, then we'll be done automatically. So let's try to do that. Of course, to work with 12, that means we need to work with two things. We need to show, work with mod 3 and mod 4, because 3 and 4 are separate. So that means we just need to show that 4 divides ABCD and 3 divides ABCD. If you can do that, then we're done. All right, now let's just take some numbers. A square plus B square plus C square equals D square. And let's try to look at this for mod 3 and mod 4. Okay, right now, let's try with mod 3 first. So if you look at this equation in mod 3, as you know, numbers in mod 3 are either 0 or 1 or 2. So if you have a square, however, the only value that it can take is 0 or 1. And the simple reason is you can always build a table, simple table here, like x and x square in mod 3, of course. So x is either 0, 1 or 2. So 0 square is 0, 1 square is 1, 2 square is 4. 4 is what? Mod 3, it's 1. So that means that the only values that x square can take are 0 or 1. So that means that these guys, each one of them is either 0 or 1. But remember that our goal is to show 3 divides A, B, C, and D. So if we have a single one of them that's 0 mod 3, then we're already done. So let's assume that no, none of them is 0 mod 3. So if we none of them is 0 mod 3, that means that all of them are 1, right? All of them should be 1. So that automatically means that 1 plus 1 plus 1 is congruent to 1 mod 3, which clearly is wrong. So that means we reached a contradiction. So that means our assumption was incorrect. So that means that at least one of them should be 0 mod 3. All right, so that means we have shown indeed that 3 divides ABCD for any values A, B, C, and D in S. Very good. We're done with that. Now let's, our goal is to try to work with 4. So now we're going to do the same thing. Let's take the equation again. Mod 4. Sorry, equals. So mod 4, the numbers, the squares mod 4, let's organize the same table. X square, 0, 1, 2, 3, 0, 1, 0, because 4 is 0. 3 square is 9, that is 1. So that means that squares are either 0 or 1 mod 4. So this thing mod 4, this thing is mod 3. So that both of them, the squares are always either 0 or 1. Okay, that's very good. So let's do a similar technique here. Right now here, if you look at this, if you want to show that 4 divides ABCD, then that means we need to either show that there are 2 even numbers, or to show that one of them should be 0 mod 4. So here, if we look at this thing here, this equation, if we have a single, either we can have a single number that's even, or if we have 2 numbers that are even, we're done. So either we have a single number or we don't have any, all of them are odd numbers. So if there was a single one that's even, what does that mean? Notice that this thing is 0. So that means that if a single one of them is even, then the rest are odd. So that means, let's say this guy here is even, then odd plus odd plus odd is going to be odd. So odd plus even, it cannot be 0. So automatically that means that this case is refused. So we cannot have a single even number. That means the only way to do it is to get let's assume that none of them is even. All right, so if none of them is even, that means all of them are odd. So automatically all of them are 1. So again, the same thing. 1 mod 4. Which is also a contradiction. So that proves that indeed 4 divide ABCD, and guess what? That means if 3 divides ABCD, 4 divides ABCD, that indeed 12 divides ABCD. Hence, that shows that 12 works Why is it the greatest? Because of this example. Like if you have something like, let's say 24, then wrong, because from here we got that 24 should divide 12, which is wrong. So that means we already done. Like by just simply dividing, like bringing this example, we showed that the greatest number is 12, and we already showed that 12 work by discussing mod 3 and mod 4. Alright, so that was like a simple question that you just use mod in it. For problem 2, it's a geometry question. So we're given here a semicircle, so just this part here, like a semicircle, with a diameter AB. Okay, they are giving us a CD which is a variable chord on the semicircle. However, CD is has a constant length, so let's call this constant length like L. CD has a constant length. Okay, okay, they're telling us that it's on the arc AB. Then we're given a point E on the diameter, that is AB, such that the two angles, like this angle here, is equal to this angle here. Okay. And then they asked us to show that this measure, CED, is constant. It's constant, that means it only depends on L. So if you give me L is 2, then we already have a single value. If it was like 3, it depends on L. It's a function of L. Okay, so let's give it a try. Of course, we have another part, but let's first of all focus on the first part. Okay, so what can we do here? As you can see, we have this condition here that these two angles are equal. So for sure we should use that. But how exactly? How exactly are we going to deal with this angle? The problem with this angle, it's not like a circumscribed angle, because if we have some angle here, then surely it's like it only depends on the length of the arc or the length of the chord. That's the same thing. And it's not also a central angle. If we have a central angle, then it only depends. In fact, like the measure of it, it's the arc itself. The problem here, we have like some circle, and we have some random thing. Okay, it lies like on some diameter, but it's not really that much important. So how can we find angles that are inside a circle? They are not like super random. Actually, you can do that. There is like one theorem that's really nice. The idea is just to extend this and extend this. In fact, this angle here, we call this A, B, C, and D. Then this angle theta, let's call it. So theta, you can find it. It's just the length of the arc AB plus, the measurement of arc AB plus the measurement of arc CD, this angle, divided by 2. This is like well known. You should keep it in mind. And in fact, we also have like another situation. Let me draw another circle. Sorry. Yes. And let's take a point outside. So what if we have something like this? So we're interested in this theta. Again, let's say this thing is AB, and this thing is C, and this thing is D. So here actually the theta for this is AB, kind of similar, AB minus CD divided by 2. So these are like nice things. They are kind of a generalization for the circumscribed and the central angles. So that means that if we keep that in mind, now we have to deal with some angle like that. So one idea we should think of is simply to extend. Like we need to extend this here and extend this here. And now we know what's this theta. So now this theta, like let's name these like C prime, D prime. Now we know that theta is equal to CD. Of course, this thing is constant, plus C prime, D prime divided by 2. So since this is constant, we need to show that this is a constant. But let's analyze points C prime and D prime. Because we just did extensions, then we already know that this here is equal to this. Okay, This is actually, if you look at it, this is really nice, because that means since we have AB is the diameter, and we took some random point on it, and you took like here, this angle is equal to this angle here, then that means C and C prime are symmetric over AB. Like this thing here is symmetric, like the reflection of C over the diameter, it will be C prime. Here the same thing, if you also reflect it over, like D and D prime are the image under the reflection over AB. This thing is really nice because that just means that this thing here is also L. So that means in fact that C prime D prime is equal to CD. So that means that this thing is just CD, the arc, the same as the arc, the measurement of the arc, the angle of it. So that automatically actually finished the question, because clearly CD, the measurement of CD, depends only on L. So that's it, like simply. We're done. We showed that it's constant. So as you can see, the idea here of our construction was simple. We wanted to handle this angle. This random angle is not like a circumscribed nor the central. So the only way to deal with it is just to like, you know, continue the diagram. Okay, next we've got part B, don't forget. The circumcircle of triangle CED, we need to show it passes through fixed point. Alright, so now we're interested in this circle. Here. This circle, we need to show that it passes through a fixed point. So these types of questions, usually the idea is simple. You need to guess what is this fixed point. And once you guess it, you just need to show that it always lies on that circle. So of course, if you have any point that lies on that, like a point here or whatever, then it's going to always have this thing is the same as the arc. This angle is going to be the same as the arc. But guess what? Think about it. Which point do you know that, like if you draw something like this, then the angle of it is going to be the same as the angle of the arc? You guessed it. That is the O, which is the center of the circle, right? So simply, if you just pick the center of the circle here, let's say somewhere here, O, we all know that simply this angle, COD, is simply just equal to CD, the angle of the arc. So that means it's also theta. So simply that's it. That means this point is O, and we already proven that. Alright, that simply finished like problem 2, which is the geometry question. So as you can see, it's not a difficult geometry question. It's really some simple stuff about just angles and cyclic quadrilaterals. Alright, for question 3, we're given a natural number n, and they're defining this function Sn as the sum of the digits. This is like a common symbol in Math Olympiad. You should be familiar with it and solve some problems about it, like sum of digits. And we need to find all natural numbers m and n such that m is less than n, and we have these two relations. If you take the sum of digits of n and you square it, you get m. And the same thing for n. N is the sum of digits of m, and then you square it. Okay, so before we start with this question, let's discuss the function Sn in general for any number. So let's say we simply have a number n that is, let's call it it's something like a0, a1, a2. I'm just writing the digit representation of it in base 10. Of course, what's the function is S of n is simply the sum of these, right? So it's an plus an minus 1, so on till a1 plus a0. So these the questions that have Sn, usually 90% of the times, they just have two ideas really. The first idea, that's really simple, you should already know it from school, is that mod 9. If you take mod 9 is really powerful, because we know that if you want to have mod 9 of a number, then it's just you take a look at the sum of digits, right? And you check them. So that means we have this very nice relation that n is congruent to Sn mod 9. So this thing is really important to keep in mind. This is a powerful tool in these types of questions. The mod 9 is probably the most important mod in these types of questions. The other thing that you should keep in mind is the size. Look at the size. I mean by size, inequalities. if you look at s, who is greater? Do you think s of n or n, generally speaking? Well, clearly s of n is too small compared to n, usually. So, for example, if you have some number, let's say, like some random number, what's the sum of the digits of these numbers? It's just like 1 plus 1 plus 2 plus 3. That's just 7. Compare 7 to this, there is no comparison, right? Like, in fact, if you look at this, you can easily build some very simple inequalities. For example, here, what is the maximum value that s of n can take? Think about it. So, like, we need to maximize the digits. What is the maximum digit you can take? 9, right? So, like, to maximize s, we just choose all of them 9, 9, 9, 9, 9. So that means this thing is always less than or equal to 9, here m plus 1, because we have m plus 1 digits. So it's m plus 1. So that means that, like, of course, this thing, where n, of course, is the number of digits, compared, sorry, here, I don't mean like the same n here. Here I should have used another, like, variable like k, let's say. K, here k. So at most k plus 1. So here, this thing, where k is the number of digits, and you have like n is this number. So that means here you kind of know that n is between what and what? Between 10 and 10 to the what? Think about it. So n is greater than 10 to the k, and 10 to the k plus 1. Because, for example, let's take an example. Here we have k plus 1 digit. So if you have like number maybe 23, it's 2 digits, right? So it's greater than 10 to the 1 and less than 10 square. So we have 2 digits. We subtract 1 here. Here is the same. Here same thing. N has k plus 1 digits. We put k plus 1 here, and you put k here. Okay. So that means like n is in this range, while Sn, the maximum that it can get is this. And of course, there is no comparison between 10 to the k and 9k plus 1. So that means, like, of course, n is way too large compared to s of n. Of course, like, this is generally speaking. So you should always, look at size, like stuff. I always like when I test my students, I simply give them some questions like this, like solve some for natural numbers, and look at their thinking here. For example, if you look here, clearly this guy here is way larger than just the sum of the numbers, right? For example, like if we have 10 times 10 times 10, this thing is 1,000, while this thing here is just 30, right? So clearly, when you like multiply stuff, it's way greater than when you add them. So that means you should always look at size stuff, like size comparison, when you work with number theory questions. Alright, so with that like in mind, like really questions that have s in them, s of n, they usually just fall in these two categories, either mod 9 or just size stuff. So right now, with that in mind, let's try to work with these guys here, and remember that n is greater than m, strictly greater than m. Okay, so let's write here what we have. So we're going to start with the solution here. So we know they told us that n is equal to the Sm squared, and that m is Sn squared, and remember that n is greater than m. So what can we work here on? This one or this one? Well, clearly we should work here. The reason is simple. You can simply create an inequality at once because n is greater than m. Then we know that m is less than s of m squared. And remember what we've just said? We've said that m is way greater compared to Sm. So clearly we're just going to do something like this. We're going to reach some contradiction here. By the way, like one thing you should have immediately noticed is that m is s of n squared. So that means m is a perfect square. Same thing for n. Like n is something squared, so n is just a perfect square. Okay, let's just keep that in mind, that m and n are both perfect squares. Okay, and right now let's return to our inequality thing. So we want to reach a size contradiction somehow. So again, how do we bound these? We need, like unfortunately, we cannot just bound it using m. We need to assume m is something. So let's say m has some like digits. In fact, we don't care really about the digits stuff. Let's just think about it as this. It's greater than 10 to the k minus 1 and 10 to the k. Here we said that the number of digits of m is k. Okay, so if it's k, then we already have this one, as we explained earlier. Again, like just for you to know, if we have two digits, let's say 23, 23 automatically is between 10 and 10 square. So if you have k, then you put k minus 1 here, and you put k here. Okay, just not to make mistakes. Okay, so if we have this, then we have k digits. So automatically we know that Sm is less than 9 times k. Of course, or equal to. So that means now we can simply create this. M is greater than what? Remember, 10 to the k minus 1. And Sm is less than what? It's less than 9, less than or equal to 9k. So that means 81 k squared. Alright, now we got something nice. So now we've shown that 2 to the k minus 1 is less than or equal to, or actually it's strictly less than, because here we have strictly less than 81 k squared. Now this is something nice. Clearly you can see that the LHS is way greater than the RHS, because like 10 to like an exponent function here, it grows larger than like simply quadratic. But of course this thing fails for small values. So here this thing fails for 1. For 2, here you have 10 to the like just 10. Here you have for sure like something greater. For 3 it also fails, because this thing is just 100, while this thing is 3 squared, 9 times 81. However, for 4 this thing is way larger. It's like 1000 for 4, and this thing is just like 16 times 81, which is clearly less than 1000. Oh, actually, wait a minute. Like this thing is 1296. So no, like this, that means also 4 fails here. Alright, so that means, but for sure 5, like 5 here will give us a contradiction, because here of course we're going to have 10 to the 4, and this thing is for sure not going to be that number of digits. So that means we've shown that k can be either 1, 2, 3 or 4. What was k? K was just the number of digits of m. Okay, very good. So that means that m is something like a, b, c, d, only a 4-digit number. And in fact this immediately gives us something nice. So Sm is like the largest value is just 9 times 4, which is 36, right? So that means, for example, if we return to our question, remember that n is equal to Sm squared. So n is less than or equal to 36 squared. And already we have m is less than n. So these guys are less than 36 squared. Now, if we remember that m and n are both perfect squares, so I believe that, you know, the best way not to forget this is simply to brute force it. So n is just, let's call it n prime square, and m, let's call it m prime square. So now let's just plug in. So that means that we already have that n prime is just equal to Sm like square, and m prime is just equal to s n prime squared. Okay, so now we just need to work with these, and we already know that m prime is less than m prime, which is less than or equal to 36. Okay, of course right now you might be like super happy, because okay, you have less than 36, so you can just try all values from 1 to 36, and for sure you're going to solve the question. However, like usually this is a bad idea. When you get too many cases, although like it's doable, you can do it, it's better to try to find some hacks, some tricks to try to reduce the number of cases. Because remember, you also like you just have just 3 hours, and you want to finish the whole paper, or like at least to solve as many paper questions as you can. So let's try to reduce some cases by using some tricks. What exactly can we do? Like, this is the only thing that we have here and here and here. Remember, right now we just used the idea of size, but remember what was the other idea that's very, very like commonly used in these questions about S, the sum of digits? Exactly, it was the mod 9, right? So let's try to work mod 9 here. How exactly? Well, the idea is simple. First of all, let's take something like this. So remember that mod 9 of this and this, when you have mod 9, then the S just drops. So automatically that means that M prime is just M prime square, and M prime is just N prime square, mod 9. So automatically that means that we can, plug one with itself and find something nice. So that means that, like here for example, M prime is N prime square, but N prime itself is M square. So that gives us that M prime is just M prime to the 4 mod 9. Okay, very nice. Now we're interested in solving this one. So to solve this one, we can just move this one here and factorize. So we know that 9 should divide M prime times M prime cube minus 1, which can be factorized like this. Square prime square plus 1. Alright, so we have this thing here. Let's look at it and find the solutions. Mod 9. Let's work mod 9. So for sure, if M prime was 0 mod 9, it's a solution. So any number that's 0 mod 9 work. What also work? So if this guy here was not 0 mod 9, like it's either divisible by 3 or not. If it was divisible by 3 but not divisible by 9, then we can actually remove it, because like if this guy was divisible by 3, then this is not divisible by 3, and this is not divisible by 3. So that means we can now just forget about this. Like right now, that simply means that multiples of 3 that are not multiples of 9, they don't work. So any number that's like 3 mod 9 or 6 mod 9 will not work. Very good. Right now we can just forget about this M prime, because now we will assume that the number is not a multiple of 9 or multiple of 3, sorry. So right now we just have this thing as remaining. Right now, like these, do they share any factor? These two things. If you know some GCD stuff, then you can easily see that like if they have a common divisor, let's say it's D, then M prime is 1 mod D, and this thing mod D is going to be 1 plus 1 plus 1, so 3 mod D. So that means that like M prime is, as we said, 1 mod this D, and this thing here is just going to be 1 plus 1 plus 1, which is 3 mod D. So that just means that 3 is a multiple of this D, right? So that means, of course, here I'm assuming that D is a prime number. So that means, yes, they might share a 3. So the only thing that they can share is a 3. So that means that we might have this situation that this thing is divisible by 3 and this thing is divisible by 3. In fact, that means if M prime is 1 mod 3, then this always works. If M prime was 1 mod 3, then this thing is divisible by 3 and this thing is divisible by 3. So 3 times 3 is 9, so it always works. So this is also a solution. But if M prime was like 0 mod 3, it doesn't work. We already said that, unless it's 0 mod 9. And if it was 2 mod 3, then this thing is not divisible by 3, nor this thing will be 4 plus 2 plus 1, not divisible by 3, it's 7. So that means that these are the only solutions, these ones. Alright, now this is the real deal. Now this is a real nice trick, because this reduces this 36 cases into a way less than that. Let's write all of the cases. So right now we're going to take all numbers from 1 to 36 that are like either multiples of 9 or they're 1 mod 3. So that means you just need to look at this set. Let's write that are numbers that are multiples of 9 first. 18, 27, and 36. This is the first set. The second set is just 1 and just keep adding 3s. 1, 4, 7, 10, 13, 16, 19, and then 22, 25, 28. Then we've got 31, we've got 34, and you've got 37. Okay, actually that's it. So now you just have these. You can just try m prime, any one of these set in this set. I don't think that will going to take too much time, because you just need to find like the square. You need just to square m prime. Once you square it, you just take the sum of the digits and look at like this number will be n. You will check that if it works or not. Yeah, like this is really doable. I don't think it's going to take like 5 minutes even. So you can try that. And here, as you can see, how many numbers do we have? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So just 16 cases, 16 numbers. As you said, it's doable compared to the 36 cases that we have earlier. So as you can see here, if you just try these, I'm already, like, of course, I'm not going to waste time right now here in front of you doing them. But if you just do them, then you're going to get that this guy here is solution, and you'll see that the solution is m prime equals 13. It's going to give you m prime. Of course, if you square this, you're going to get this number. If you add the digits, you're going to get 16. So that means that m prime is equal to 16. M prime, sorry, 16. So that means that what is m and n? Like, the only solution is this and this, and we're done. That's the only solution. All right. So as we saw here, the only ideas that we did is size, as we mentioned earlier, and after the size, we just used mod 9 to, like, cancel or reduce the number of cases. Alright, for problem 4, we have a geometric question. So we've got two circles, omega 1, omega 2. They are intersecting, and their center is O1 and O2. We have a random line that intersect both circles. The first one at point AC and the second one at point BD, such that A, B, C, D are collinear in that order. So as you can see here, I've just drawn two circles with centers O1 and O2, and I just choose this random line here. This random line and intersect like A, B, C, D in the same order that they mentioned in the question. Okay, continue reading. We have a perpendicular bisector of AB, and we also drew the perpendicular bisector of CD, and each one of them we intersected with the circle at like the points P, Q, and RS. So as you can see here, what I simply did is I took this thing AB, this segment, and I took the perpendicular bisector of it, PQ. I did the same thing for CD, this thing. I took the perpendicular bisector of it here. It cuts at R and S. So that just means that these guys here, 90 degrees, perpendicular bisector, clearly. Okay. Next, they're just asking us to prove that the midpoints of PR, QS, O1, O2 are collinear. So here I just took the midpoints, as you can see here, like M, K, and N. We need to show that they are collinear. Alright. Of course, like the first thing to solve a geometric question, you need to draw a diagram. The diagram is a little complicated, so let's say how you can construct your diagram precisely, in a precise way. So of course, you catch your compass and draw two circles with two, like the centers are already there. You take a random line, so that you take A, B, C, D on that order. Of course, like the rule of thumb that I always going to tell you, that first of all you draw a simple diagram on your draft, like a very small diagram, very quick, like something like this. Like this, you put the centers, you take, a random line maybe, and then you just like choose your point like this, and just see do all your points fit inside the diagram, because sometimes you might like have an intersection like this, so it's outside your paper. So you don't want to spend tons of time drawing this diagram and then you end up with the points outside the diagram. So first of all, always rule of thumb, draw a simple diagram, check all your points, and then go and draw the accurate diagram. Okay, of course, after you draw the two circles, to take the random line, you can easily, construct a perpendicular bisector of this and this by simply finding the midpoint using your ruler, and then just drawing a perpendicular on it, and then everything is already there. You just putting the midpoints, you can use your ruler to get it. So now you've got a very precise diagram like this one here, and now we can think about the question. Okay, so our goal is what? To show that these guys here are collinear, the midpoints. First of all, let's try to analyze our diagram. Remember that these guys here are both perpendicular. In fact, we know that this is equal to this, and this thing is equal to this, and this thing is equal to this. Of course, that already tells us that this is a trapezoid, because these two are parallel. So in fact, this line here is also parallel. If we just discuss the line MK, forget about point N. If you look at MK, it's the mid base of trapezoid PQSR. So it's the mid base. So we need to show that this midpoint of O1, O2 belongs to this mid base. So if you really think about it, if you have a trapezoid and you take the mid base, then any point on the mid base satisfies what property? It simply satisfies the distance from here to here is the same as the distance from here to here. Any point on the mid base. So that means that it's actually enough for us to show, if we take N and we draw perpendicular here and drop perpendicular here. So now this thing is 90 and this thing is 90. Remember, we don't know that N lies on MK. In fact, usually I advise my students to make it a dotted line so that they don't make the mistake of doing a circular proof. Sometimes your mind automatically assumes that it lies on the segment and you get a circular proof, so you get 0 points. Of course, you don't want to do that. So I'm just going to here put a dotted line, and now this thing here, let's call name these guys here something like X, Y maybe. And now our goal is just to show, this is equal to this. If you can show that, then we're done. Okay, how exactly can we show that? Don't forget that we already have something nice, which is this is equal to this. So we kind of have this shape here, two parallel lines, and something like this here, and take the distance here and the distance there. And this thing is 90, this thing is 90. These two guys are parallel. We know that this is equal, this is equal to this, and our goal is to show that this is equal to this. Okay, what can we do? Let's look at our diagram here. So right now, how can we show that this distance is equal to this distance, nx and ny? There is really not that really multiple of stuff that you can do here, because you simply have this point N is a little weird since it's the midpoint of O1, O2. How can we deal with it? But it satisfies that it's the midpoint of O1, O2. So maybe we should look for some congruency here, since nx, we want nx to be equals to ny, and we have no1 is equal to no2. So one idea you might think of is to draw O1y and to draw O2x and try to make them equal. This thing is really not that clear here, So what can we do? So here, there is one thing that's really you should notice when you're dealing with this question. Look at it, at this question. You have two circles, you have the centers, and you have chords, right? You have tons of chords. You have like A, B, C, D, the whole thing. Like it gives you some chords, like AC is a chord, BD is a chord. You have PQ is a chord. You have SR is a chord, and you have the centers are there, like the centers of the circles. And you have also tons of midpoints, like this guy here is a midpoint. This here is a midpoint. So one idea you should think of is to try to get these like involved. Since you have the center, you can take the center and drop perpendicular bisectors to the chord, right? Because we know if you drop from the center perpendicular to any chord, then it's going to bisect it. So this thing, let's us try to think of this thing. Like if I try to drop a perpendicular here, and like I will get the midpoint, right? And also the same thing if I drop a perpendicular here. These are also like midpoints. Like let's right now call these temporarily like maybe C and something like T. So of course, because these are perpendiculars, if we zoom here, if this is 90, this thing is 90. So now if you look at this, this is a rectangle, right? This shape here is a rectangle. So of course we need to define this point as well. I'm not sure what can we call it. Maybe R. Oh, actually we have R already. Let's call it something like, okay, what's a letter that we haven't used yet? Maybe G. So we have GTO1Z is a rectangle. So G, what is G? G is the midpoint of AB. T is the midpoint of GC. So in fact, what is the length GT? Like it's midpoint and midpoint. To see what is GT, you can like simply take point A and scale, like take a scale of 2 times 2. So like this is kind of homotopy, you can say. So like Y will be sent to point B and T will be sent to point C. So that just means that GT, this length is half of BC. Very nice. So GT is half of BC, and so that means O1C is also half of BC. Very good. So O1C is half of BC. Now if you do the same thing exactly for O2, because you know you have also another center, and you drop this here, this perpendicular here, and drop this one as well here. Let's call this thing maybe I, and this thing maybe also U. So again, we also have a rectangle, and the same idea again. Like if you look, this thing here is going to be half of, like if you take the homotopy at D, it's going to send I to C, and it's going to send U to B. Then that also means that this length is just half of BC. So that also means that OI is half of BC. So guess what? These are equal. Very nice. So that gives us something nice here. Returning to this simple diagram, since this one is O1, this one is O2, or maybe the opposite. If you drop this and drop this thing here, perpendiculars, we have just shown that these two are equal. All right, our goal is to show the green thing. So do we have that already? Think about it. These two, like let's try to use congruent triangles here. So right now, if I just draw this thing here, these two triangles are congruent because of SAS, right? SAS. You have like a side here, a side there, side here, a side there, and you also have that angle is the same. Okay, very good. Next, since these are congruent, then that just means that these are equal. In fact, of course, this angle is equal to this angle, and that angle is the same. So right now, if you look at this right triangle here, and that right triangle here, they're both right triangles. The hypotenuse is the same in both of them, and you have the angles are the same. So by ASA, they are congruent, and hence the green, like we have the green thing, is like they are equal. So that simply means that indeed what we needed to show, that is nx equals ny, is indeed correct, and that means that we're done. The midpoint of O1, O2 lies on line MK. All right, again, like a quick recap of what we did here. We looked at our question. We noticed that PQSR is a trapezoid very easily. So we said that we need to show that n lies on the mid-base. What does that mean? That means we just need, like if we look at this simple shape, this thing is of course here our n here. We need just to show the green like equality here, but we know that n is the midpoint of O1, O2. So when we draw that, we looked at our diagram, we did not really have like a direct way to do that. However, when we looked again at our diagram and noticed that we have the centers and you have tons of chords, so you should always think about dropping perpendiculars from the center to the chords. This is like, you know, a general thing, because you really need to do something. You should not just keep looking at the question, maybe do angle chasing. This will not always work. You need to do some constructions, and these constructions they're usually really logical. They're not something magical. So here you have centers, you have chords. So just drop. If you drop these perpendiculars, you get something nice. So we just did that, and we noticed that we got some rectangles here, also rectangles here. And when we analyzed what is this thing, can we find the length of it? Well, it's joining two midpoints. So one idea is to find that. You just, you know, take one point like A and do a scaling times 2. So you figure out that they are actually half of BC. Similarly, you get the other one is half of BC. So that just shows that if you drop from O1 perpendicular to that chord, and from O2 perpendicular to that chord, then they're equal. Now we can add to our simple shape here these new perpendiculars here and here, and they're equal. Now we can easily show that actually these two quadrilaterals are congruent using some simple stuff, and that just shows what you wanted, that the green equality, and that means that we are simply done. Alright, question 5. We have two numbers, n and k. They are positive integers. N is greater than k, greater than 1. We need to find all positive reals, a1 till an, that satisfy the following equation. So we have this sigma, the sum of roots of k ai to the k minus over k minus 1 ai to the k plus 1. This thing is really ugly. That thing is equal to sigma ai, sum of ai, and that is equal to n. So basically we have two equations here, two relations. We know that the sum of the numbers is like equal to n. So this is number 1. This thing is a nice relation. We know the sum of the numbers. But the problem is the other one, which is too ugly. That is sum of the root k ai to the k over k minus 1 ai to the k plus 1 is equal to n. How can we deal exactly with this thing? So first of all, like something that you really need to keep in mind. When you see these types of questions, they are giving you n numbers, n unknown variables, and they're giving you a single equation to solve them. How is that? Like usually what we learn, or what we know, like logically, like for us to find n numbers and n unknown variables, we need to have n equations, right? N equations with n variables. Okay, this is solvable. How can we solve one equation with like n variable? Well, that means that 99% of the times this is done through inequalities. Because with inequalities you can actually solve tons of variables with one equation. Like the simplest example, if you have something like maybe like you complete it to a square, something like this. If you have some squares and their sum is 0, then you already know that all of these guys are 0. So this is one equation with 3 variables. We already got that here, x equals y equals z. So the only way like to solve these types of questions is to think about inequalities, or at least it's always like a good idea to think about inequalities here. Okay, and if you've been following the inequality course, quality tutorial we're uploading on the channel, of course you should be doing that. Like here, this thing, if you want to deal with it, with inequalities, of course we have a roots here. We have a numerator and denominator. You can easily see that the denominator is really the ugly thing here. So what kind of inequalities can we apply here? Remember that k is an integer. So when we say like k ai to the k, then this thing is ai to the k plus ai to the k times. Same thing for denominator. You have ai to the k plus ai to the k, so on, k minus 1 times. So if you look here, for sure the denominator is uglier, and we know from like the inequality playlist that we should always try to look at the ugly stuff and try to make them beautiful, right? So that means what can we apply on the denominator? If you have ai to the k, ai to the k, so on, ai to the k, how many times? K minus 1 times, plus 1. Well, an immediate thing that you should think about, an immediate inequality, is the AMGM, right? What happens if you apply the AMGM? If you apply the AMGM, you're going to get, we have k numbers, so k times the root of k, ai to the k, how many times? K minus 1. And of course, this thing is just equal to k ai to the k minus 1. Alright, now this is a nice thing. Now we're done with, like, this thing has just become this thing. And now guess what? The k will cancel with the k, and ai to the k will cancel with ai to the k minus 1, and we will just have remaining ai. Okay, now this thing is a real beautiful thing. So right now that means that, by the way, here we did this thing is greater than something, but no, we should flip it because it's in the denominator. So that means that this thing is less than sigma of the roots, right? So that we've just shown that sum of the roots is greater than n, or equal to, of course. So we have this, and remember we have this. Now also from our inequality playlist, you should recall that how can we link between sigma ai and sigma root ai? Well, the best way is through Tito's lemma, right? Tito's lemma, or you know, the angel form of Cauchy. So basically you can just say that sigma ai, which is basically the sum of ai squared, you know, now you have it like the Tito's form. So now if you apply Tito's lemma, you're going to get this squared over n. Alright, but this thing is equal to n. So that just means that n is greater than sigma root of ai, because like if you just multiply here, you're going to get that. But we already know it's greater than n, so greater than n and less than n, so it's equal to n. So that means is equal to n. And when does the equality hold in Tito's lemma? The equality holds when all the numbers are equal here. All the numbers are equal, and we already know their sum is equal to n. So that just means that like all the numbers are 1. So ai equals 1 for like any I. So that just means that like all the numbers are 1. Of course, you can easily check that this satisfies what we want, because here this thing will be n, and this thing here will be like k over k minus 1 plus 1, so it's k. So k over k is 1. So sum like 1 plus 1 plus 1 n times, so it's indeed n. So that just means that the only solution is all the numbers are 1, and that finishes it. So as you can see, the main idea, you really need to think about inequalities, because you have tons of variables, unknown variables, and a single equation. And once you think about inequalities, it's really simple. You really just want to get like beautify the ugly thing, apply some inequality there. AMGM is the first thing that should like come to your mind here. Once you do it, you automatically get sum of roots, and you already have the sum of the numbers, so immediately Tito should come up to your mind. Of course, if you haven't watched the inequality playlist, then I highly recommend to do that. At least finish watch the first 3 videos about AMGM. First, watch also the 3 videos about the Cauchy. These are really important inequalities that you should keep in mind. Alright, now let's move on to the last question, question 6. Alright, our last question, problem 6. We need to consider 16 points in a 4x4 square grid, as you can see here. We need to show that if they are giving us that 7 points are colored blue, so 7 random points are colored blue, and we need to show that there exists an isosceles right-angled triangle whose vertices are blue. Alright, so right now we have 16 points, and we're going to have 7 points that are blue. We need to show that there exists at least a single triangle that's right angle and isosceles. Okay, so let's start here. First of all, of course, we'll assume the contrary, that we don't have any isosceles triangle, right angle triangle, and we will try to reach a contradiction. As you can see, we have tons of cases here, so we need for sure, we don't have really a method just to discuss all cases at once. We really need to try to find some tricks to reduce cases. By the way, if you're familiar with the pigeonhole principle, you should know that probably we're going to use something like that, because the pigeonhole principle, when you distribute some stuff over some stuff, and you have something like at least 2 or at least 1 or something like that, then usually the pigeonhole is really used in these types of questions. So you should keep that in mind and try to work with this question. First of all, let's try to analyze this question. So our goal is to find isosceles triangle, right angle triangles like this, right? So that means whenever you have 2 points, they are blue, then automatically this point cannot be blue, right here. The same thing for this point, it cannot be blue, right? In fact, same thing if you have 2 points opposite. If they are 2 blue, then this cannot be blue, this cannot be blue. Very nice. So that means that, of course, this thing generalizes not just on neighbors, but even if it was greater, maybe here, if this was blue, this was blue, then automatically you will refuse this one. This cannot be blue. Same thing like here. So that just means that we should be working with squares, because if you consider squares here, then automatically if you have 2 points, you cannot have a third one. So any square can have at most 2 points, 2 blue points on it. So probably if you think about squares, then it's going to give you something nice. So for example here, if you try to divide your diagram into squares, maybe one idea is try this. The simplest thing ever. So now you're going to distribute 7 blue points over that, over 4 squares. Then you cannot have, of course, 3 in any of them, so at most 2. So that means the only way is 2, 2, 2, 1, right? So let's say 2, 2, 2, and 1. 2 points there, there, and here 1 point. However, one thing here is that, here we just picked one case actually, or let's say one division of squares. However, actually when we'll be working with the question, if you think about this division here, your mind it will automatically grasp these simple squares. For example, let's say we're discussing some case and we said this blue is this blue, your mind will automatically delete these. However, your mind will not be able to delete complicated squares. So actually we don't just have these simple squares, we have other complicated stuff. For example, let's say you got this point and this point. Your mind will not find it immediately that this point is deleted. So the point here I'm making is that we should try to do our division for more complicated squares. that our mind will not catch, so that we will be working on these, and our mind will automatically catch the small ones automatically. Okay, so let's try to find another division. So I want you to try to find like a division that has some complicated squares in, that our mind, like, it's kind of impossible to catch immediately, and like try to think about it. So right now that division is something like this. We can choose the central square. We can choose then this one here. Of course, I'm trying not to make the points there, because otherwise we will miss them. However, of course, they all lie there. So this is one. Okay, this is two. Where are the others? You can see them here. 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 And let's use green. Now the remaining. There. There, and finally that one. Alright, so these are some nice, again, 4 squares, 7 divided by 4. So like we're going to have 2, 2, 2, 1. Very good. So that means like each square is going to have at least a blue one, right? Of course, like this one, like we said, 2, 2, 2, 1. Like we have many cases, either the one is the central one, or one of the like red, green, or black. We will not be discussing these cases. We'll just take the really the very obvious thing, that we at least have a one blue in each one of the squares. So which square we should be working with? Which one do you think we'll be using like this point? Like, the answer is simple. If you look at the central one, the central square, if you try to use it, it's going to be like the most useful, because it's going to be giving you lots of info. However, if you pick like one of them there, it will not be giving you that much info really. So if we'll be just trying to catch one of these. So right now I'll be deleting these. So I will assume that this one, without loss of generality, is like picked this point here. And right now we have just shown that we have at least one central, like 1 point on the central square. So I just assume without loss of generality that it's here. Now, remember I just told you that we have now tons of info, like on this diagram. How exactly? Well, now if you look here, you can, for example, say that this and this cannot be paired. Like, we can pair them, because if this is blue, then this cannot be, right? So, this is one info. So we can actually do kind of a pairing system here. So if we try to pair, let's do that. If I give this one, and this one, and this 2, and this 2, then automatically you can say that I cannot pick 1 and 2 at the same time. I cannot have a 1 and a 2 at the same time. If I have 1 and a 2, then I will be having an isosceles triangle, a right angle triangle. So like this is really nice. Same thing here, 3, 3, 4, 4. I cannot have 3 and 4. So 1 and 2 we cannot have, and 3 and 4 I also cannot have. So in fact, if we just like right now forget about the whole diagram, just think about this 3 times 3. If we try to think about this one right now, how many points can we have here? If we have actually, like, of course, forget about this point here. If we have like other 3 points, then that means, remember, you cannot have 1, 2, 3, and 4. So you can either have one of these and one of these. Maybe like, let's say 1 and 3 just. Here you have 2 of these and 2 of these. So if you have 3, then by pigeonhole, you have actually that, let's say like you're distributing 3 over 2. So at least 2 1s, or 2 3s, or 2 2s, or 2 4s. So without loss of generality again, let's assume that we have maybe 2 1s. So we'll have these, this and this. Of course, right now our assumption is that we have three other points on the on this, inside the square. This one I'm not counting it. I'm assuming that we have 3. So if we have 3, then like, okay, right now we have all of that. But right now you can easily see that this one cannot be there, this one cannot be there, this one cannot be there, this, they all cannot be there. So a contradiction. But you might say, okay, my case is not symmetric because I should also take a diagonal. Maybe they are on the diagonal. You're right. Let's also discuss the diagonal. So maybe this one, let's say 3 and 3. But right now, again, the same reasoning. This cannot be there. This cannot be there. Like, by the way, if you're asking why this cannot be there, then just look at this triangle. Okay. Like, again, this, they all cannot be there. So a contradiction, right? Because we said we have 3. So we have still a remaining 1. So that means we cannot indeed have 3. Very good. So at most, we can have 2. Other than this blue one here. So that means that inside this 3 by 3, we can have at most 3 ones. The one originally here and like 2 others. Very good. But the question is, what if we have a single one? Can we have a single one here? So basically like this one and another one. Well, if we have here just 2 inside this one here, then that means that like we have still 5 as remaining because we have 7, remember? So if we have 5 as remaining, and this 5, that means they're going to be distributed here, right? How many points do we have here? You can count them. 4 plus 3, they are 7. So if you want to distribute 5 over 7, okay. Right now, remember that we have this point. Can we use it to get some info here, like some pairing here? Well, sure, we can. For example, you can look at this isosceles triangle. So that means we can also do pairing here. So let's do the pairing again. I'm going to like use the same numbers here. Let's say 1, 1. These are paired. Can you find other pairings as well? Yes, we can. We have 2 here and 2 here, because this also gives you like an isosceles right? So we have 2 and 2. We have 3 and 3, and this one like is solo here and only. So right now we also established a pairing. We cannot have 2 ones here, like 1 1 or 2 2 or 3 3. But remember, we have 5. We said that we have 5 points. So if you distribute them like over them, 1 will catch the 4. We still have 4. 4, you're distributing them over 3 numbers. You're going to get one number that's going to have 2, which is a contradiction. So that means that right now we have shown that this cannot be just 1 and it cannot be 3, so it must be 2. So here we have exactly like 3 numbers, this one and like another 2. That means like there we have just 4. Okay, very good. So that means right now we have established that. Okay, let's keep this one, we already have it. We have shown that inside this one we're going to have 3 points, and here we're going to have how many points? 4 points. 4 points. Very nice. But again, if we have 4 points here, we'll be just working here now. If we have 4 points, and remember we cannot have 2 points in the same number, we cannot have 2 points in the same number, then that means this for sure is colored blue. And if this is colored blue, then automatically we can delete this, because otherwise we'll have an isosceles triangle. And automatically we can delete this, otherwise we have an isosceles triangle. Sorry, like this. Then that means we killed all the ones, like 1 1, it's killed. So that means now we got a contradiction, because like right now the 4, okay, we have 3, and we're going to distribute it over only the numbers 2 and 3. 3 points here, and we're going just to distribute them on the 2s and 3s here. This automatically gives us a contradiction, because that means by pigeonhole that like 2 2s are there or 2 3s are there, which is a contradiction. We said that we cannot have 2 2s nor 2 3s. So that indeed finished the question. So again, let's wrap up what we did here. First of all, we started by dividing like the question into squares, right? The grid into squares. But we said that we should not try like obvious squares that our mind immediately can catch. We should try more complicated ones, and our choice was really like good, like this one, the big one, and like these other ones as well. When we did that, we saw that we must have one in each one of them, right? It was like 2 2 2 1. So we said, instead of discussing cases which one is the one, let's just take the most obvious info that we can extract, that if we can just have one of them. And the most useful square of the 4 ones that we draw was the central one, because the central one gives you tons of info, because it's in the center. It will give you tons of pairs, as we saw in the question. So we just assume without loss of generality that it was this guy here. Then after we took that, remember we said it's going to give us tons of info, so we started just writing this info by doing the pairing system. The pairing is really useful. Usually, like if you know some pigeonhole questions, if you have solved some pigeonhole, you have some experience with pigeonhole, then you should get these ideas quickly, like these pairs, dividing into squares, into pairs, because this is really very common with pigeonhole. And exactly this is what we did here. We just did this pairing, this nice pairing. We saw that we cannot have a 1 with 2 or a 3 with 4. So that immediately gave us kind of something to do with. So we cannot have other 3 points, because if we have 3 points, then we're going to get a contradiction with the pigeonhole. And if we just have a single point, then now we can move to this part here. We're going to have 5 points. If we have 5 points using our pairing again, and by the way, the numbers, of course, like above and below, they are unrelated. So again, we got a contradiction. So that means exactly we're going to have here 3 points and here 4 points. And again, using these 4 points again, we just by working here with pigeonhole again, it also gave us a contradiction, because once you have this 4 here, then it kills all the ones, which means you're just left with 2 and 3, and that gives you a contradiction. Yeah, that's it. We are done. Alright, as a summary, this paper was really nice. The questions are not that super hard, but of course, given that the time is limited, then of course it's a challenging paper. First of all, question 1, this was like a very easy one. You simply just catch an example, m divides 12, and automatically your first guess should be 12 itself. And to do that, you just work with mod 3 and mod 4. If you're comfortable with mod, this should be not difficult at all. The next question, it was an easy geometry question. The main idea was we need to work with an angle that's not central and it's not circumscribed, but it's related to the arc. So how can we do that? You simply just extend. Once you extend, then automatically you're just going to see that you have this reflection, like CD and C prime D prime. They are reflections of over AB. So you'll automatically find out that it's just the angle is the same as the angle of the arc, and automatically you will remember which point gives you the same angle as the arc. It's the center, so that immediately kills B as well. Next, for question 3, this was a nice question. If you have some experience with the sum of digits of a number, these questions, as we said, have 2 ideas: either playing with mod 9 or playing with size stuff. You can always maximize using the 9, like 9 plus 9 plus 9, and as we see, we can link it to the number of digits. So this is exactly what we did there. We used this idea that m is less than s of m all squared, and we established some bounding, and easily got that k can be at most 4, and hence the sum of digits can be at most 36. And then we just use the idea that they are perfect squares, and we then have 36 cases to discuss, which is too much. You should not immediately, when you get some limited number of cases, you should always try some tricks like playing with mod. And this is exactly what we did here. We played with mod 9, which is the most suitable one, and immediately reduced our cases into just 16 cases. Now this is kind of doable. We can try these cases. Remember, they are not really hard to discuss, each one of them. Especially if you did that IOQM paper 2023, it was tons of cases. and tons of calculations. So compared, with this one is really easy to discuss cases here. Okay, so right now we just found the answer. That was the idea. Next, question 4, the geometry question. This was like a really nice question, not that easy, as you can see here. The idea was we noticed that we have a trapezoid and that mk was the mid base, so we need to show n is on the mid base. What does it mean to be on the mid base? It means that your distance from the first base is the same as your distance to the second base. This is exactly why we draw that line yx. Now, like when we look at this figure here, we don't really have a clear way to do it, like how to show that. So we need to do something else. When we looked at our diagram, we saw that we have centers and we have tons of chords. So one direct thing we should think about is to try to drop perpendiculars from the centers to these chords, because you're going to get some nice midpoints and some rectangles. And once we did that, we immediately noticed that we can like find the length yt. It's just half of vc, and they established that the distance from O, the center, to that base is the same as the distance from the other center to the other base. That immediately, now when we did it here, that gave us congruent quadrilaterals, and that immediately killed the question. Next, for question 5, we just saw that the idea is simple. You have n variables, unknown variables, and you have a single equation. The only way to do it is with inequalities. If you have been watching the inequality playlist, there should be a piece of cake for you. Like you can easily play on the denominator using AMGM. Since it's the ugliest thing, you should try to do that. And then, of course, you just find a relation between the sum of the numbers and the sum of roots using Tito, and get a contradiction. Finally, question 6 was tons of cases. So to deal with it was really simple. We just try to actually, it's not that simple, to be honest, but we just try to like cut it into squares, right? Divide it into squares. We try to do with the non-obvious squares, and immediately got like a central square. It should have at least a central like blue point. Once you have that, we play on the 3 times 3 that has this point on it. Once we're like here, we see that we cannot have 3 and we cannot have 1, so it must be exactly 2. So here we have exactly 2 in addition to the central one, and on the outer one we just have 4. And then like simple discussion will show you that even this does not work. So that's it, my friends. That was the paper, RMO 2023. Like if you like the video, please don't forget to share it with your friends, and like and subscribe to the channel. And in like addition to that, join the Discord channel or server, and see you guys in other videos.